In this video, we are going to talk about the ideal gas processes. We will approach a few questions and we will construct a matrix that will help us remember the details of these processes so that we'll be ready to work with them whenever we need to. So in the first question, we see that a sample of monatomic ideal gas is taken through an adiabatic compression. It is then brought into good thermal contact with the environment and expanded until the gas returns to its original pressure. So which is true? Is the thermal energy higher than the initial, lower, or the same as the initial? Alright, so we might remember that an adiabatic process is one in which the cylinder is well insulated and does not allow any heat transfer from the environment or to the environment. So let's go ahead and write that down. So a well insulated cylinder will allow us to accomplish an adiabatic process. It might also be good to accomplish that process fast. Let's think about an adiabatic process, how it relates to the first law of thermodynamics equation, delta ETH equals W plus Q. And that's the W meaning the work that the surroundings does on the gas. So delta ETH equals W plus Q. Well, Q is going to be 0. Like we said, the cylinder is not going to allow any heat transfer. So delta ETH will equal W. So let's draw in here just a little miniature PV diagram about what that might look like. So if these dashed lines equal isotherms, our process might look something like this. This being the initial here and the final here. Okay, so let's think about the second half of this problem. The part where the cylinder is brought into good thermal contact with the environment. So what process is accomplished through good thermal contact? Well, we might remember this is how we do an isothermal process. So good thermal contact, and it might help if we do this process very slowly. So there's going to be no change in temperature, and there will be no change in thermal energy. So if we know delta ETH will be 0, and we know that because ETH is going to equal n number of particles times the average kinetic energy of those particles, and the K average only depends on temperature. Temperature is not changing. So if delta ETH equals W, or equals 0, then W gas will equal Q. So we can just go ahead and draw out this PV diagram. And this time, we know it's just going to stay right on that isotherm. And let's come down here, and now we can draw these two processes on the same PV diagram. So let's say this is our initial point here. So we'll just call that A. And then we do our adiabatic compression, so volume is decreasing. And then let's do our isothermal expansion. And we're going to expand isothermally until we get down to the same pressure. So we're going to actually have to go off of this diagram here, but something like this. See? And so let's see if the final energy is greater or less. So look at how large this volume is and the same pressure. It must be that the final thermal energy is higher than the initial. And so we can conclude that because delta ETH in the first part, the adiabatic compression, equals W, and it must be that the surroundings are doing positive work on the gas. And we know that because it's being compressed. So if we just think about this cylinder here, here's a piston. And so there's going to be a force from the atmosphere and a force from the gas. And the displacement, because it's a compression, is going to be down. So the work equals force times distance, is going to be positive, and the work gas will be negative. So delta ETH is positive for the first part, and delta ETH is 0 for the second part. So it only makes sense that the final thermal energy will be higher. Additionally, we can conclude that the product of P times V at point C is higher than the product of P times V at point A. And how do we know the product of P times V is going to be related to the total thermal energy? Well, we can think about the ideal gas law. And we know that the number of moles isn't changing, and the gas constant is certainly not going to change. So we can see that temperature will vary with the product of P times V. And we know that thermal energy is going to depend only on temperature. So let's go ahead and move on to our next problem. So now we have a piston on a cylinder containing a sample of ideal gas that is allowed, and the piston is allowed to slide without friction. Heat is then added to the system until the thermal energy of the gas doubles. So which of the following is correct? Is the work done by the gas on the surroundings positive? The work done by the surroundings on the gas positive? Is Q negative, or does delta ETH equal Q? Well, let's try to remember which type of process is accomplished by allowing the piston to slide without friction. Well, I think that's a constant pressure process. So let's write in here, we accomplish this by allowing the piston to slide without friction. Okay, and so let's think about the first law. So delta ETH equals W plus Q. Well, in this case, I don't think there's much we can do with the first law. So let's see, what would this look like on a PV diagram? Well, the pressure is not going to change, so it's just going to be a horizontal line of some sort. All right. So let's start looking at these answer choices. So is the work done by the gas on the surroundings positive? So let's see, is work gas positive? All right, well, again, let's think about this first law of thermodynamics. And like we said earlier, this W is really the work that the surroundings does on the gas. So maybe we can draw this piston. Okay, and let's see. So this is the initial position of the piston, and then heat's added. So this is going to be the final position of the piston. It's got to be an expansion, because if the temperature, the thermal energy doubles, the temperature must be increasing. So the product of P times V must be increasing. So it must be the case that this piston moves upwards. And now let's see, so this displacement here, is that going to be in the direction of the force from the gas or the direction of the force from the environment? Well, it looks like it's in the direction of the force. So it must be that this W, the work done by the surroundings on the gas, is negative. And again, the work done by the gas on the surroundings, well, this is positive. Okay, so we see that option A is correct. And we could maybe just be done here. But let's think about the other options and why are they wrong. So the work done by the surroundings on the gas is positive. Okay, well, that's the opposite of true. So we know that in this case, the piston moves up, and the displacement is therefore in the direction of the force exerted by the gas. So work gas is positive and work of the surroundings on the gas is negative. C, Q is negative. Well, the problem will tell us that that must be wrong because heat is added to the system. So Q must be positive. And delta ETH equals Q. We know that's not going to be correct because the piston will slide. And delta ETH equals Q, well, does that remind us of a constant pressure, or does that remind us of something else? Perhaps another process that we'll visit momentarily, a constant volume process. So delta ETH will equal Q for a constant volume process. And let's talk about why that is. So in a constant volume process, there will be no displacement of this piston at all. So without displacement, work must equal 0. And therefore, delta ETH will equal Q. Now, for our final question, we want to look at this process below. So it appears this didn't copy properly, but if we draw in here, this is in fact a PV diagram. And here, I think this is the initial. Let's just ignore this. And this is the final. And if we want to know how to accomplish this, do we perform positive work? Well, change in volume, constant volume, there's not going to be a displacement. We just talked about this. It's not going to be a displacement, so there's not going to be any work involved in this. Do we allow the piston to slide without friction? Well, what might happen if the piston slides? The volume will change. So that can't be it. Do we lock the piston in place? Okay, well that sounds like a good contender. So let's add that to our matrix. So to accomplish a constant volume, we lock the piston in place. And let's just finish our matrix here. And why is D wrong? Well, that describes an isothermal process, so not the constant volume process featured above. So hopefully this video has been helpful in your understanding of the ideal gas processes. And it might be a good idea to either copy this matrix down or at least take a screenshot of it, and you can use it when doing practice problems so that when you get to the exam, you will be ready to answer any questions on the ideal gas processes.